In this video, we're going to take a look at the parabola. Um, Instead of thinking of the parabola as the graph of a second degree polynomial function, though, we're going to take a look at the parabola as it pertains to conic sections, so our double napped cone, and how to generate the parabola from that. So we're going to start with a geometric definition. And so geometrically, so this would not involve the coordinate plane at all. So geometrically, a parabola is just the set of all points in the plane that are equidistant from a fixed point, which we call the focus, no surprise there, and a fixed line, which we're going to call the directrix. So it's all points in the plane that are exactly the same distance from some fixed point called the focus and some fixed line called the directrix. So basically, to define a parabola geometrically, you've got the plane, two-dimensional. Um, you got our two-dimensional space that goes on forever in both directions. And then you pick a point and you pick a line. And as soon as you pick a point and a line, that defines a particular parabola. So as always, I've got some visuals to help us with that. So let's go ahead and take a look at those. Okay, so here I've got a parabola that's graphed in the plane. So this black curve right here is our parabola. Probably recognize it from our algebra courses. Then this blue point F is the focus. And this purple line down here is our directrix. So I picked a point, called it F. I graphed a line. And as soon as I picked that point and that line, that defined this very particular parabola. So the geometric definition says that this is a parabola as long as every single point on the parabola is exactly the same distance from that point called the focus as it is from this line called the directrix. So I had GeoGebra calculate that distance. So from this point to the focus is 2.83 units of length. And then that point down to the directrix is 2.83 units of length. They're the exact same distance. And even if I move it, they're still the same distance. And if I move it all the way down here, they're the same distance. Same distance. Same distance. So this parabola, what it is it's a collection of points that are exactly the same distance from this point called the focus as they are from this point, or this line, I'm sorry, called the directrix. So that's what our geometric definition is trying to say. It's all the points that are the same distance from some point called the focus and some line called the directrix. Now, if I pick a different point for the focus and a different directrix, I likely will get a different parabola as long as the focus and directrix are further apart from each other or closer to each other. I would get a different parabola. So let's go take a look at this idea of picking a focus and a directrix. So I'm going to have GeoGebra plot a point. I'm just going to pick a point here. So I'm going to have that be my fixed point, the focus, and then I'm going to have it draw a line so there's my line. I can have it be a different color so we can see it a little bit better. So that would be red. So there's my line, call that the directrix, and then I can have it create a parabola. So there's the parabola that's created from that focus and that line. However, if I move the focus closer to the directrix, I get a different parabola, a more narrow parabola. If I move the focus further away, I get a different parabola that's much, much wider, W-I-D-E-R, wider. So the closer the focus and directrix are, the more narrow the parabola, and the further they are away, the wider the parabola is. And you can have a parabola that opens either to the right, you can have one that opens to the left. Um, I could change my directrix to be horizontal. Then you would have a parabola that opens upward, or I could have a parabola that opens downward. So we're only going to look at 4 types of parabolas, ones that open up, ones that open down, and then as we saw before, ones that open to the right and ones that open to the left. Those are the 4 we're going to take a look at. Okay, so now let's bring the coordinate plane into this, and let's write down an algebraic definition for these 4 types of parabolas. So under normal circumstances, I would derive these, or I would derive at least one of these for us. But for time reasons, keep the video short, and the fact that we're doing some e-learning instead of the traditional, we're not meeting in the classroom. I'm going to go ahead and save that for now. So let's go look at the algebraic definition for these 4 types of parabolas. So you're going to see a lot of similarities with the algebraic definitions of the parabola as you did with the ellipse and hyperbola. So parabolas don't have centers. You already know that from algebra. They don't have centers, but they do have a vertex. So the vertex this time is going to be our H and K instead of the center, because they don't have a center. Now, ellipses we had the major axis, and it was either horizontal or vertical. And then hyperbolas had the transverse axis that was horizontal or vertical. For a parabola, again, as we remember from algebra, they have an axis also called the axis of symmetry. And the axis of symmetry is either going to be horizontal or vertical for the ones we're going to be interested in. So let's say that the axis of symmetry is parallel to the x-axis, which would make it horizontal. Well, algebraically, if it's going to have a horizontal axis of symmetry, then the parabola is either going to open to the right or it's going to open to the left. So if it opens to the right, its algebraic definition would be y minus k quantity squared equals 4 times some constant a times x minus h. And then this is going to open towards the right. So it's going to look like this. Well, I could do a better job than that, I guess. It's going to open towards the right. And it's going to have a horizontal axis of symmetry. But we're going to look at 4 different kinds of parabolas, ones that open to the right, ones that open to the left, ones that open up, and ones that open downward. So to save time, I'm going to go ahead and fill out the rest of these, the remaining 3, and then start up the video again, and then you can just pause to write them down. You don't have to watch me write all these out. Okay, so here we have all four algebraic definitions that we need to be familiar with. So as you can see, they correspond to four different types of parabolas, ones that open to the right, ones that open towards the right, ones that open towards the left, ones that open upward, and ones that open downward. Those are the four types that we need to be familiar with. And then notice the vertex is just going to be HK for all of them because they don't have a center. No center, just a vertex. And again, the vertex, as we'll draw pictures of all this with all our vocab here in a sec, but vertex, as you might remember from algebra, is where the parabola, the curve itself changes direction, or where the axis intersects the parabola. That's the vertex. So it's that blue dot in my little sketches over there. And then the equations themselves are fairly easy to get the hang of. Um, if if the quantity that has x in it is being squared, those are the ones that open up and down. And the way to remember that is those are the ones you're already familiar with. So back in algebra 1 and 2, mainly algebra 2, you guys did parabolas that opened up and down because those were functions. Those are polynomial functions of degree 2. And those had x being squared. So those functions, y equals ax squared plus bx plus c, x was being squared. They were the ones that opened up and down. And then if you contrast that with the other two, notice that the quantity with y is being squared. So if y is being squared, they open to the right and they open to the left. So if x is being squared, they open up or down. If y is being squared, they open to the right or to the left. Now, how do you know which ones open up and down and left and right? Well, again, I argue that's fairly straightforward also. So notice this has a negative. Let's get a highlighter here. Notice we have a negative 4. There's a negative 4 here, and it opens to the left. And remember, on the coordinate plane, if you move left on the x-axis, those are negative numbers. And then notice down here, there's a negative 4, and that's the one that opens downward. And if you move downward on the y-axis, so in the typical way we draw the coordinate plane, if you move downward on the y-axis, those are negative numbers. So the two that have a negative 4, one of those opens left and one of them opens downward. So getting the hang of these four equations really isn't terribly difficult compared to some of the other things that you'll be asked to do in your mathematical career. So you're basically just looking to see is y squared, then it opens left to right. If x is being squared, it opens up or down. If there's a negative 4, it either opens down or it opens left, the two negative directions on the coordinate plane, the way we typically draw the coordinate plane. Okay, so you'll notice that the only constant besides the vertex is this a value. There's just an a. There is no b or c like we had for the hyperbola and ellipse. So what we're going to do next is draw a picture, and we're going to label all the vocab. We're going to get a hang of all the vocab, and then we're going to define what this a is, what distance this a is. And you might be able to guess because it's very, very similar to the other curves that we call conic sections that we've already studied. So let's go ahead and let's do that. So let's do the vocab first. Let's do the vocab first. So there's going to be a fixed point called the focus. Then there's going to be a fixed line called the directrix. And then we're going to have our actual parabola. Now mine's not going to be geometrically perfect, so please don't pull out a ruler, measure it, and say, well, that's not actually a parabola. It probably isn't. Okay, we just want to label some vocab here. Just get some vocab. So this point right here, the point that's kind of quote unquote inside the parabola, that's the focus. The parabola kind of hugs That's how I've always thought of it, kind of hugs the focus. So this right here is the focus. This red line is called the directrix. Red in my picture, of course, it doesn't have to be red. And then the black curve itself is the parabola. And then the line that contains the focus and is perpendicular to the directrix, that's called the axis of symmetry, or just axis for short. So if you just want to call it the axis, that's fine. Its main name is the axis of symmetry, because if you fold the parabola along that line, the two halves match up, as you probably remember from um, your algebra days. And then the point where the curve itself changes direction, or another way to think of it is where the axis intersects the parabola, that is called the vertex. So that is our vertex. Now, when we go to graph a parabola, we're actually going to do it in a rather quick, albeit not super accurate, but good enough for us. We're going to graph it using something called the lattice rectum. So um, one more bit of vocab we're going to put on here. Let's see if I can come up with a good color for it just to make it stand out. Let's see here. Let's kind of do this bright pink. See if you guys can see that. So when we go to graph these parabolas by hand, I'm going to use something called the lattice rectum to do it pretty quickly. And what the lattice rectum is it's a line segment. It's not a whole line, it's a line segment. And basically, it's a line segment that's parallel to the directrix, containing the focus whose endpoints are on the parabola. So for our picture, it would look like this. It would be this line segment here. So notice that line segment is parallel to the directrix, because this is a right angle. It contains the focus, and its endpoints are actually on the parabola. They're actually on the parabola. Now that line segment is called the lattice rectum. That line segment is called the lattice rectum. So if I go to label that here, so this is a line segment, and it's called the lattice rectum. And I think that's Latin for erect side, is where that name comes from if you're curious. Now notice the only thing that's actually the curve itself is the parabola. So this black curve right here, this black curve right here, that's the only thing that's actually the parabola. Everything else helps us define or graph the parabola. But the only thing that's actually the parabola is this black curve in my picture. So the lattice rectum helps us graph it, the focus helps us define it, the directrix helps us define it, and the vertex helps us graph it also because it's on the curve. So that's all our vocab. You're going to hear me use those words over and over and over again. Axis, parabola, focus, lattice rectum, vertex, directrix, all that. You're going to hear that over and over and over again. Now, what is A? What is A? So our vertex is HK. That part's not complicated, I don't think. But what is A? Well, it turns out A is a very useful distance that we're going to use over and over and over again. So let me draw another parabola. By the way, this could be any orientation. It doesn't have to just be upward opening. I'm just drawing it upward because it's easier for me to draw. What A is, here's the directrix for that parabola. You know, I guess I could do a little bit better job of drawing that. So there's my directrix. Here's the focus. And A, it turns out, A is the distance from the focus to the vertex. That distance is A. But remember, the focus and vertex, um, the vertex is the midpoint of the focus and the directrix. So if I come down here, this distance is A also. So A is how far apart the vertex and directrix are, and how far apart the vertex and focus are. Now, A is also something else. See if I can draw this parabola a little bit more accurately. You'll see why here in a sec. So I've got the focus and directrix pretty far apart. So my parabola should be a lot wider. So see if I can get this thing to look a little bit better. There's my parabola. Now, the other thing that A is useful for is it turns out that when you use the lattice rectum, so that would be this line segment here, it turns out that this length is 2 times A, and since it's symmetric, this length is 2 times A. So the whole lattice rectum has a length of 4A. So the length of the lattice rectum is 4 times A. So if you go back and look at our algebraic definitions, that right there is the length of the lattice rectum. That right there, that right there, that right there. Now, I know some of them are negative. You would ignore the negative because it's a length. But that number, 4A, is sitting right there in our equation. That's why it makes it so easy to graph these when it's written this way. So kind of like our other equations, it's written in such a way to make graphing a lot quicker. Okay, so length of the lattice rectum is 4A, and then those that just prefer verbal descriptions, A is the distance between the vertex and focus, or vertex and directrix. All right, so that's going to be what lets us work with all these parabolas in a fairly efficient manner. So let's give this thing a try. Let's find an equation of the parabola whose vertex is 0, 0, and whose focus is 3, 0. All right, well, let's see. Our vertex is 0, 0, so h is 0, k is 0. And then 0, 0, and 3, 0, those are on a horizontal line. So we have a horizontal, so these lie along a horizontal line. So we have a horizontal axis. And then 0, 0, and 3, 0 are 3 units apart. They're 3 units apart. So go away. So since 0, 0, and 3, 0 are 3 units apart, we know that A is 3. So this also tells me up here, this also tells me that A is 3 because the vertex and focus are 3 units apart. Okay, so if the focus is to the right of the vertex and this thing opens right, so the focus, I don't need red anymore, do I? So the focus is to the right of the vertex. So that means my parabola opens towards the right. So this thing tells me this. Because remember, the parabola likes to hug, kind of wraps its arms around the focus. Okay, so I know it opens to the right, so I know which equation to use. So it's going to be y minus k squared positive 4a x minus h. So now let's plug everything in. So it'd be y minus 0 squared, 4 times 3, x minus 0. So we'd get y squared equals 12x. That's the equation for that parabola. Now it says graph the equation, but I forgot to delete that. We're actually going to graph it in the next example just to save space. So we are going to graph it, just not right here. We're going to graph it right down here. Just forgot to delete that. So we're going to graph the following: y squared equals 12x. We did all the work for that above it. I just wanted more room to be able to graph this thing, so I made it a separate example. So here's the y-axis. Here's the x-axis. Now notice that a was 3, so if you go back up here and look, this is the length of the lattice rectum. So my lattice rectum is going to be 12 units long. So keep that in mind when you make your coordinate plane. Got to do 12 units of length. So we're going to need our tick marks pretty close together here. So um, so I'm going to go down to -8 and up to 8. Back to -5, should be able to fit everything. We'll see if I need to go farther than 8. If I don't, I'll erase the rest of my x-axis and shorten it up a bit, but let's see. All right, so my focus was at 3, 0. That's the focus. My vertex was at 0, 0. So there's our A, right? Here's our A. A is 3 because the vertex and focus are 3 units apart. And then my directrix should be 3 units behind that. So my directrix, I should be able to go 1, 2, 3, and that's my directrix. There's the directrix. So now to get the graph of the parabola, all I have to do is use the lattice rectum. So remember the lattice rectum, it has the focus on it. I double whatever A is, and I go that many units on either side of the focus to get 2 more points on the parabola. Remember the endpoints of the lattice rectum are on the actual parabola right here. There they are. So for this one, to graph this thing, all I got to do is I have to double whatever A is, and if I double it, it's 6. So I'm going to go up 6, down 6. Remember, the vertex and these 2 points are all on the parabola. So all I got to do to graph the parabola is draw the shape of a parabola going through those 3 points. That's why it's not perfect, but it's good enough for us. So my lattice rectum, I used that idea to know that this was 6 units of length. That's 6 units of length, which is 2 times A. And then this is 6 units of length. That's also 6 units of length, which is 2 times A. And 6 plus 6 is 12, exactly the length that we saw right there. So graphing these actually goes pretty quick when you get the hang of it. So plot the focus, plot the vertex, double whatever your A is, and either go up and down if it opens to the right or left, or go left and right if it opens up or down, as we'll see when we do more examples. So I don't really need, I didn't really need all this x-axis here, but that's okay. You don't know till you get graphing. All right, let's try another one. Let's find the vertex, focus, and directrix of this parabola and graph it. So since y is being squared and 8 is positive, this one opens towards the right. Let's write it in the format that we prefer. 8 would be 4 times 2. So we know that h is 0, we know that k is 0, and we know a is 2. Right, so those are all right there. Boom, boom, boom. H, K, and A. So my vertex is 0, 0. The focus, well, remember, we're opening to the right. So if I'm at 0, 0, and the focus is going to be to the right of that, 2 units. So it's going to be 2, 0. Then my directrix would be 2 to the left of that. So starting at 0, 0, I would go left 2 and be at negative 2. So it's going to be x equals negative 2, vertical line. Right? If you open to the right, your directrix is vertical. If you open towards the right, your directrix is vertical. All right, so there is the 3 things they asked for. Then they said to graph it. So let's go ahead and graph it real quick. We'll graph it a little bit quicker this time. Focus is at 2, 0. Directrix is at negative 2. Vertex is at 0, 0. And then if I double A, I get 4. So I'm going to go up 4, down 4. I'm going to carefully draw shape of a parabola here. And boom, there's our parabola. All right, let's try another one. This time, notice x is being squared. X is being squared, and this is negative. So x is being squared, and this is negative, so it opens downward. So it's going to look like this. There's the directrix, and then our parabola opening downward. It's going to basically look like that. So let's write it in a form that we prefer. We see that h is 0 and k is 0, and we see that a is 3. So there they are. There's our important numbers. A can never be negative. A is a distance. So keep the negative with the 4. So the vertex is 0, 0. The focus, well, remember the focus, the parabola likes to hug the focus, so it's going to be downward. It's going to be downward from the vertex. Downward from the vertex. So it's going to be 0, negative 3. And then our directrix is going to be horizontal, so it's going to be y equals, so we go up from the vertex. We go up 3 units. So it's going to be y equals 3. We'll see that when we graph it. So let's go ahead and graph this one. So our vertex is at 0, 0. There's our vertex, V. And then our focus is down 3. And our focus, you went down 3 units to get the focus. Then we go up 3 units to get the directrix. And then we use the lattice rectum to get the rest of the parabola. So if I double A, I get 6. I get 6. If I double my A value, I get 6. So I go 1, 2, 3, 4, 5, 6 to the right of the focus, 6 to the left of the focus. And those are the endpoints of the lattice rectum. So my parabola is going to go through those. So there's the parabola right here. All right, so there's one that opens downward. Let's see. Let's go ahead. There's nothing special about that next example. Let's go ahead and save some time. Let's do this example here. So find the equation of a parabola whose vertex is at 0, 0. So h is 0, k is 0. Its axis of symmetry is the x-axis. Its axis of symmetry is the x-axis. So it's got a horizontal axis. And its graph contains negative 1/2, 2. Negative 1/2, 2. So it doesn't say that's the focus or vertex. It just says that it contains negative 1/2, 2. So our vertex is 0, 0. So if I sketch this real quick, this isn't my final official graph, but its vertex is 0, 0, and its axis of symmetry is the x-axis. So this parabola is either going to open this way or it's going to open this way. It either opens left or opens right. It's got to be one or the other. So that narrows down my equations. My equations, since it opens left or right, it's got to be y minus k squared equals 4a x minus h, or it's got to be y minus k squared equals negative 4a x minus h. It's got to be one or the other. So let's plug in everything we know. Let's plug in everything we know. Let me save some room here. So let's plug in everything we know. So it's going to be y minus k squared equals, we don't know if it's plus or minus 4 just yet, and then x minus 0. But we actually know a coordinate on the actual parabola. That's just a generic coordinate that's on the parabola. So let's plug that in. So that would be 2 minus 0 squared. Let's see what we get. We get 4 equals, let's see. So if I multiply both sides by, let's get rid of this negative 1/2. Let's multiply both sides by negative 2. And then divide by 4, I get a. Basically, it has to be 2. Right, I guess we don't really need the plus or minus. We can take care of that later. That's probably just making things more complicated than they need to be. So if we solve that, we get a is negative 2. So let's go back and plug everything in. So we'd have y minus h squared If a is negative 2, we'd have negative 4 times 2x minus 0. I know a was negative 2, but remember, we'd like a to be positive, so it's a distance for us. So the negative can just come out in front of the 4. Let's see, we get y squared equals negative 8x. So let's check and see if that gives us everything we want. We definitely will have h and k be 0, but let's double check that negative 1/2, 2 is actually a point on this parabola. So if x is negative 1/2, then this becomes 4. If I plug 2 in there, 2 squared is 4. True. True. 8 can't be positive because if I plug negative 1/2, 2 in, that'll be a false statement. So we don't want 8 to be positive, we want 8 to be negative, because then when I plug in negative 1/2, negative times a negative is a positive, and y squared is a positive. So this is the equation we want. So it's going to open left. We said it could open left or right. We weren't sure. But using this point, it has to open left, right? Because negative 1/2, 2 is up here somewhere. So it's got to open left. Okay. Then it says graph it. So let's go ahead and graph this thing here. Make a little bit of room so we have somewhere to graph it. I'll graph it over here. Let's see, vertex is 0, 0. We know that A is 2, so I'm going to go to this direction to get the focus. Then I'll go to this direction to get the directrix. All right, notice that A is 2, right? We got it right here. And if we double that, we get 4. So I'm going to go up 4, 1, 2, 3, 4. Go up from the focus, down from the focus. And then we can draw our parabola. So there's our parabola there. All right, let's take a look at the next one here. Find the equation of parabola whose vertex is negative 2, 3. So this time, h is negative 2, k is 3. And then the focus is at 0, 3. So this vertex and this focus, you go negative 2, 3, and 0, 3. These lie along a horizontal line. So we have a horizontal axis. The focus is to the right of the vertex. So our focus is to the right of the vertex. So our parabola opens towards the right. So we're going to have y minus k squared equals 4, positive 4, times a, which we haven't found yet, x minus negative 2, h is negative 2. Let's go get a. Let's go get a. So negative 2, 3, and 0, 3, those are 2 units apart, so a is 2. So if I go plot those, negative 2, 3, and 0, 3, those are just 2 units apart, so a is 2. We'll see that when we plot them or graph them if you're a little unsure of why a is 2. So a is 2 here. So we get y minus 3 squared equals 8x plus 2. So there is our equation, which was requested. Now let's go graph all this. Okay, so our vertex is at negative 2, 3. Our focus is at 0, 3. And then that makes our directrix. Since A is 2, I'm going to go 2 to the left of the vertex. There's my directrix. It's back here at -4. Now I'm going to use the endpoints of the lattice rectum to graph the parabola. So A is 2, so if I double that, I get 4. So I go 1, 2, 3, 4 up, 1, 2, 3, 4 down. And there's my parabola. So that's the first parabola we've done whose vertex is not 0, 0, but that's okay. It's no big deal. It all works the same way. So vertex is right here. These are 2 units apart. These are 2 units apart. So that's A. Then you go up 4 and down 4 to get the endpoints of the lattice rectum to help you graph your parabola. Sketch that thing in and we're good to go. Okay. Next up, what if it's in general form? So this is general form. Recall that general form is when all the variables, all the terms of the variable are on the left side and the right side is 0. So I guess more specifically, everything's on the left side and the right side is 0. That's general form. Everything's kind of multiplied out too. We don't have anything factored. But we want things to be factored. So we're going to have to complete the square here. This is not the first time we've done this. So let's group everything up. Notice that x is being squared. So I'm going to complete the square with my x variables. Y is not being squared, so there's nothing to do with that. You can't complete the square if you don't have a quadratic term anywhere. So let's complete the square on this part. So we divide 4 by 2 and square it, we get 4. And I can't add 4 to the left side without keeping everything balanced by adding 4 to the right side. So I end up with x plus 2 squared minus 4y equals 4. But that's not quite the way we want our equation written. So let's keep going. I'll add 4y over here. The right side still doesn't look like what we want for us to be able to graph it quickly. So what we want to do here is we want to make sure that this variable y, so if you go back and look, scroll all the way back here. Notice on the right-hand side, this variable, this variable, this variable, and this variable, they always have a 1 in front. 1, 1, 1, 1. I need those to have a 1 in front. So if we go back, I need my y to have a 1 in front. So I'm going to factor out this 4. Now I would factor out whatever is sitting in front of that variable. It doesn't matter what's sitting there. I would factor that out. It could be a fraction. It could be an odd number. It could be a prime number. It doesn't matter what it is. It doesn't matter if it's the greatest common factor. To make this thing be in what we call graphing form, I need to factor that out so that the coefficient of y is 1. So now it's written exactly like I want. We know that h is -2. We know that k is -1. I know a is 1 because they're all sitting right here. And I know that this thing opens upward. So let's actually answer the question. The vertex is going to be -2, -1. I go left 2, down 1. And the focus, well, A is 1, so I'm going to go 1 unit. This thing opens upward, so I'm going to go 1 unit up from the vertex to be at -2, 0. My directrix, I would go 1 unit below the vertex. And since it opens upward, it's going to be a horizontal directrix. So again, it would look like this. There's my directrix. There's my parabola. Focus is going to be up here. So my directrix is going to be y equals -2 because I'm going to go 1 unit below the vertex. So it's going to be y equals -2. Then we're going to graph this thing. So let's graph this thing real quick. Try to get it graphed down here. So y equals -2 is my directrix. My vertex is -2, -1. Focus is -2, 0. And then A is 1. So if I double that, I get 2. So I'm going to go 2 to the right and 2 to the left to get the endpoints of the lattice rectum. And then draw my parabola in. Okay, last one. Let's do an application problem. So it says the cross section of a particular satellite dish is modeled by a parabola. So what they're telling us there is if this is the side view of the satellite dish, it's going to look like a parabola. Now, it'd be a satellite dish, so it wouldn't go on forever in both directions. It would actually terminate somewhere. So that's the side view of the satellite dish. The signal that emanates from the satellite strike the surface of the dish and are reflected to a single point where the receiver is located. If the dish is 8 feet across at its opening and 3 feet deep at its center, what position should the receiver be placed? Okay, so basically they're saying that out in space there's a satellite orbiting the planet, and that satellite is going to send signals down to Earth, and those signals are going to hit this dish, and they're going to bounce off the dish, and they're going to bounce to a receiver placed inside the dish. If you have a satellite dish on your house, go look. There'll be a little arm with a receiver at the end of it collecting all the signals. Now, because the reason they use a parabola is the geometric definition of the parabola says that as the signals come in, every single signal that comes in will always be bounced to the focus. That's the beauty of this shape, this geometric shape, is that whatever the focus is, these signals are always going to bounce to it. So even if the signal comes in here, it's going to bounce to the focus. Even if the signal comes in here, it's going to bounce to the focus. Every signal from the satellite orbiting the Earth that hits your dish will be bounced to the focus. So they just need to put the little receiver there, and it'll collect all these signals. So um, let's use what we now know algebraically about a parabola to see where we should put that receiver. All right, so here's the, remember our satellite dish doesn't go on forever. It's kind of it's part of a parabola. So let's label everything they told us. They said that the dish is 8 feet across. So that tells us that this distance is 8. And they tell us that it's 3 feet deep. 3 feet deep. So this distance is 3. So let's put this on the coordinate plane. So if I put this on the coordinate plane, I can put this anywhere I want on the coordinate plane, but I think you'd agree if the vertex are at 0, 0, that would make everything a little bit easier. So why don't we go ahead and put this point here at 0, 0. Then let's finish drawing the rest of it. There's the rest of this parabola. Now, since we're 8 feet across, I know this coordinate and this coordinate. I go up 4 and down 4. This has got to be up here at 4. It's going to be down here at -4 because I know I'm 8 feet across. And then I know that let's see, what else do we know? We know this distance is 3, so I know that that's 3 and that's 3. So I'm going to go 3 to the right, up 4, 3 to the right, down 4. And that takes care of the two measurements they gave me. Now I just need to figure out where's this focus located. Where is this focus located? Well, let's use our algebraic definition. We know that this thing opens to the right. We know this thing opens to the right the way that we placed it on the coordinate plane. We could have placed it any way we wanted, but I put the vertex at 0, 0 and had it open to the right. So this would be y minus 0 squared equals 4ax minus 0. Now I know that 3, 4 is a point on the parabola, so I'm going to plug that in. So 4, 3, gets 16 is 12a, so a is 16 twelfths, or a. I can take a 4 out of both of those. So a is 1.3 repeating, or 4/3. So we're going to place the receiver on a line directly. We're going to place the receiver on a line 1.3 repeating feet directly above the lowest point of the dish. It's kind of hard to describe, I guess, but basically we want to place it about 1.3 feet repeating. You have to round that, of course, in real world measurement, but when I place the receiver on a line 1.3 repeating feet directly above the lowest point of the dish. Kind of hard to describe where that is. If you actually had the dish in front of you to look at, it'd be a little bit easier to explain. But that's where they should put the receiver to collect all the signals that come in and hit that dish.